So let's start. Hello, everyone. This is called a doctor session where I will be talking about some very recent work, recent as is last week work that I did, sort of looking at the specific NASA Earth Science HDF5 files and comparing their original versions versus the cloud-optimized HDF5 versions. And cloud-optimized is in some ways, I'll mention that. So yeah, as I said, it's very early, and I also show some statistics that I'm trying to derive to compare these files and what's going on inside those files that may be helpful when trying to decide what needs to be optimized, cloud optimized in these files. So the data, in this case, the HDF5 data comes from this global ecosystem dynamics investigation instrument, which is installed on the International Space Station. And picture is worth 1,000 words, and animated pictures are worth thousands by thousand times more. So I found a video on this mission, this instrument's website, so I can show you just to get an idea. I hope you see it. You know, we start with a dramatic zoom to the instrument where it's mounted on the International Space Station. But what I really wanted to show you exactly how it works. So now you're going to see these red lines. These are the laser beams that this instrument emits down towards the Earth. And there are 8 of them, and 4.2 kilometer width. If you cannot see, it's too small. And basically, this is what it's meant to measure. So the structure of the vegetation underneath. That means, obviously, if there is nothing between the instrument and the Earth's surface, where there is something like clouds or something, well, then obviously it's not going to work. And so this instrument is on the International Space Station, and so it kind of orbits between, I think, plus and minus 55 degrees latitude, because the space station doesn't really go to higher latitude in orbit. And it's been in use since, I think, yeah, there it goes, 2019 some point. Why this data I'm losing? Well, the data, the fundamental instrument is the LiDAR, because there's a laser, there's a pulses being emitted, and then the waveform that comes from the reflected object are being measured. And so fundamentally, it belongs to a LiDAR instrument. And the files and the volume of data is pretty sizable. And these files, as they're being generated, as I said, the HDF5 files have a lot of data in them. I think what I received are samples of level 1B, level 2A, and level 2B processing product data. And what those levels represent depends on satellite agency, but most of them agree on certain general principles. For NASA, for example, level 1B are essentially measured data that's converted to some physical units. So it's not anymore in counts, or in digital counts of some instrument. It has some physical quantity, and also the geolocation of those measurements is known. So that's level 1B. That's sort of the lowest level of satellite data if you are essentially satellite remote sensing scientist or anyone who wants to use satellite data. That's usually lower than that is not really useful. The level 2A and level 2B are a bit more specific to NASA, but I'm going to focus on level 2A because that file has the largest amount of data in it and is the largest of all of them. And so per NASA's definition, level 2A data is essentially the data from level 1B plus a lot of auxiliary information. In this case, there's something like ground elevation, what is the highest and lowest surface return values or elevations within the viewing angle of the instrument, and all those kind of additional information that help define the context for understanding the data. And so, as I said, I got both level 1B, level 2A, and level 2B sample files. And I zeroed in on level 2A data because it's about 3 to 4 gigabyte files. And these files are at best one orbit of International Space Station, which means it starts and then full orbit comes back to a similar position on Earth. So satellite data are very rarely all in a single file. And so there are probably thousands of these files, each for one orbit, that exist. And so the interest of the people who contacted me with these sample files is that they are currently, like a lot of NASA science enterprise, is moving into the commercial cloud. So they would like to try and make these files as user-friendly for scientists global, worldwide, as possible. And they are now experiencing issues of these files not really working well in some cases. So they wanted me to take a look and see what can be done. And part of what I wanted to talk about is I'm trying to develop certain metrics and statistics that would give me sort of a high-level overview of the situation in the file, certain settings, storage settings for data in the file. And this is, as I said, work in progress. I have not settled yet on any of these, or maybe something better or different done. But what I do have now is I basically have this Jupyter notebook where I try to derive a bunch of storage settings for each chunked data set. And for example, this is the file here. I'm highlighting it. Doesn't, the file name follows this, you very often opaque file naming conventions, but it is a level 2A file, as they say, and version 2, as you can see here at the end of V0002. And so I run it and I collect a bunch of chunk statistics. So I'll run this Jupyter notebook, and so we can go through it to run ourselves. Hopefully there are no errors. But there we go. Excellent. So where we are. Yes. So when I go through this file and I collect this chunk data set info, I turn it into a pandas data frame, easier for analysis. And it turns out in this file, there are 400, just under 4,200 datasets, chunked datasets in this file, which is quite up there, even for NASA science files, although they're known to have a lot of HDF5 datasets in them. But also what I failed to mention, typically these files are produced with the same code. You just sort of, conveyor belt production. And so having a sample file and looking just a single file is pretty good enough indication of everything else, because there are not going to be a case where some of these data sets are not going to appear on some other level 2A file, or that more will appear in some other level 2A file. These are things set in stone, and these files are just emitted whenever new data comes along. So as I said, this file has quite a lot of chunk data sets, and so I try to what I collect. Where I collect a bunch of things, I obviously collect their path, because that's how I differentiate between HDF5 datasets. I also collect how many chunks are actually in the file for each dataset. I also collect the chunk size in bytes, not chunk shape so much, because chunk size in bytes is more useful to me, at least for now. I actually also collect the actual number of bytes of this dataset that are in the file. And I also do this chunk shape ratio, which is essentially a quotient between the chunk shape and the dataset shape. So this, for example, this first case, for example, means that effectively one chunk is essentially 89% of entire dataset. That's how it's defined. And so that kind of information gets selected, and then I analyze a bunch of things, obviously, here. So one of the things I do is I do how many data sets have certain sizes, certain range of chunk sizes. And, I show here. And I'm not going to go through all of this, but the very interesting things that, 1,100 chunks have less than 1,000 bytes chunk size. Now, those are, and the reason why I'm interested in this information is because essentially anything below 1 megabyte in chunk size is kind of a questionable size for cloud optimized performance, because these chunks have to be retrieved or processed individually, decompressed and everything else. They cannot be just lumped together and processed in one pipeline. Usually that's too much work to get one chunk and to process it for fairly little amount of data. And so forth and so forth. But there are some chunk sizes that are above 10 megabytes, which is an interesting also case. So this file has everything inside of it. And then also I do these chunk shape ratios, also how many, how they are, and this file is pretty uniform in that way, that we have just 88 data sets that are between 5 and 10% of chunk to the data set size, shape, sorry. Whereas most of them are 25% and more compared to entire data set. And some other things I collect, for example, how many chunks are actually stored in a file. And as you can see, there is a lot of data sets, almost 3,000 of them, that have not more than 9 chunks, between 2 and 9 chunks in the file.
Hey, Alexander, can you just go back up? So it's 1,152 one chunk data sets. They keep going up a little bit more. So basically, like all your small data sets are just, the chunks maybe had appropriate chunk size, but they just didn't put a lot of data in it.
Well, yeah, I don't, I'm not looking how much data and how much is fill value, for example, in those, data sets. What I just look is how they're defined. So, for example, this means that the chunk size in bytes of these 1,100 things is less, somewhere between 1 byte and 1,000 bytes chunk size in bytes, uncompressed.
Okay, but that's the actual chunk size, right? Not the defined chunk size. Okay.
Yeah.
Got it.
Where was it? Yes. Yeah, so here, for example, we have almost 3,000, up to 9 chunks maybe per file. There is no more. There isn't more. Essentially, seems like 99 or less chunks is the highest number of chunks per data set in this file that is stored. And then I have some other options that I can use if this file is in some way cloud optimized, and specifically in the cases that it's paged aggregation file. Then I can derive some other things, statistics that I can probably show here since I was talking about so much. But here's an interesting thing that I did. I looked specifically into exactly chunk sizes for all of them, and I count how many cases I have on specific values. So you can see that I have 104 data sets with chunk size of 4 bytes. I have 1,048 data sets that the chunk size is only 8 bytes. That's like, that tells you this, what I said, just templated production of data. This is definitely something that, should not be done. But there is interesting findings.
That's all your small ones. That's 1152. That's all your small ones.
Yeah. I know.
Yeah.
But I mean, these are really not small. This should not be done.
Yeah. Terrible idea. But yeah, people are creating data sets and they're putting like 2 things in it, right? Like small.
Yes, but there are some interesting finds. For example, there are 432 data sets that have 8 megabytes in chunk size. And there are 96 with 16 megabytes. And then 48 with 20 megabytes and something. And there are 48 of them with 40 megabytes, which is also something that is now very interesting. This is way above a dataset chunk cache for this thing. The chunk cache of the library. And I don't think that library right now will send any warning if you basically open this data set and you're having a 1 megabyte chunk cache and you're going after 40 megabyte chunk size, or those kind of things. So that's one of the things I was thinking about. Can the library actually be more proactive and saying, look, it's you do you, but it's mine to tell you that there is something, that you should pay attention to, and that kind of stuff. Because again, I don't know that people will go down the level and figure out why they're having. I mean, I'm just saying, these are not the people who spend too much time optimizing these things or paying attention to these things. But anyway, so this is the last column I just wanted to show you. This is where I say, okay, so what are the data sets actually that have chunk size of 40 megabytes and up? And this is, these are their path names. I just wanted to see what they are. And RX, I know that it means received waveform or received signal. And the beam, as you can see, these groups names, beam 000 and whatnot, those are the numbers of those 8 beams of the instrument that they're shooting down individually. And anyway, so that's that. If I put in here cloud optimized version of this file, just to show you some, and I know that this is, I want this one. And then rerun these cells again below, all recycling below, yes. So what shows up here, I covered those previous ones, but these are the new ones in cases of these file pages. And here, I basically count how many data sets fall in how many file pages. So here, almost 3,900 data sets have all their chunks in one file page. Not the same file page, but one file page. And there are 296 that have that their chunks are in 2 file pages, but there are now, for example, data sets that have their chunks in 5 or more pages. And the reason why I'm interested in this is because in the case of these paged aggregated files, the library reads data per page. So this tells me an indication that if a library gets one page, that there are a lot of data sets that will be immediately satisfied with all the chunks in their file. But that there are going to be some data sets that will require up to 5 or more data reads to get their data, if that's what the application requires. Just some indication, how we stand with that. And then this one's page spread anomaly. It's something that kind of I try to define, which means that if I take the entire storage size of a data set in a file, that this takes into account the actual bytes of each chunk. And then I say, okay, what's the file page? Then I say, well, this data set could fit into a single file page. And if it doesn't, how many more pages this data set, the chunks of this data set are spread around? And so I count these anomalies, as I call them, which probably anomaly is maybe a too strong a word, but that's what I was kind of thinking about. So this is this row here, it's kind of useless. I have to change the way I describe it. But basically, what this means is that what I showed here, for example, that there are essentially, for example, here one. Oops, sorry, that didn't go the right way. Where is this? Yeah, this is back here. So this one, that I have essentially three additional pages. So one data set is spread across 3 more additional file pages than what his entire storage size would require compared to the current file page size. Anyway, enough of that thing. I'm trying to see if there are maybe more diagrams that I could include and graphs and things that explain to people, but this is something that I try to develop both for me, but maybe for some other people to try to get a sense what to do. The final thing I wanted to show you is when these people who contacted me, they maintain a number of Jupyter notebooks that they showcase how this data can be processed and do some things with this JEDI is the pronunciation of the acronym of this instrument. And I took these tutorial notebooks and I kind of removed the stuff that are not really relevant to this data access. And then what I also did was I put this time. This is a Jupyter Notebook cell magic command. And what it does, it basically gives you a runtime of that cell. And so I put these things in, and I just ran these cells again, just changing where those files are. And I had 4 cases. I had then the original file in a local file system. I had this page, the aggregated version, into a local file system, and then I put both of these files into an S3. And so I basically was comparing the execution. And so obviously I have not, this is what I've done last week, so I haven't really looked closely, but I can go through here a little and just show you some kind of interesting results. So opening a file, original file, in S3 with ROS3 VFD of the library, complete time is about 285 milliseconds. If I look at the same thing with the page aggregated file, it's 272 milliseconds. So it's milliseconds, but not bad at all. Where I really notice the difference first time is here, because this command in H5Py basically means show me all the children, the names of the children in the root group of this HDF5 file. So for example, this to be done for the original file, it took 121 milliseconds. With the page aggregated file, it took 171 milliseconds. So, still not bad. And the biggest, sorry, why am I sorry? I forgot, that's not the same thing. This is the, no, it is, maybe. Yeah, no, it is, yes, it's right. This one was interesting to see, compare them. Yes, for the metadata, which is another group, as you can see here, it's a group inside of the root group. To get its content, it took 166 milliseconds on the original file and only 386 microseconds for the page, the aggregated file. But that's, I don't want to bore you anymore with this kind of thing. It's difficult to follow. The biggest difference immediately that came, and I expected that obviously, was for this command or for this cell here, which basically goes through the entire file, tries to identify HDF5 datasets in it, and then pull their names out, and then print. And that's the last one. Printing is an easy one, but basically remembers the names of all the HDF5 datasets in the file. So this page, so cloud optimized HDF5 file, let me put it that way, it's easier to follow. So the cloud optimized HDF5 file took half a second, basically, to do this. For the original file, it was taking 8 minutes and 25 seconds. And that's the first, it just clearly shows you the benefit of cloud optimizing HDF5 file. And the reason for this is really because with the cloud optimized file, the entire content of the file, the information about everything that's in the file and many other stuff besides the data is sort of in a single block in the file. And so the library gets that in a single request and then caches it on its side, and never again have to go and request the additional information from S3. Whereas in this case, for the original file, it constantly has to go and request small bits of file. So this is the first obvious benefit of cloud optimized file. For other things, I haven't really, as I said, gone through this very clearly. The next one is a now we're starting reading the data, and this is where the chunk sizes, the chunk cache, and all the other things come into play. And I haven't really tried to learn enough about the file content so that I know what are the chunk sizes of these data sets, for example, in the file, and try to see, what may go on there. But the original file is about 200 milliseconds. The page aggregated file is about 255 milliseconds. So it's there, but a bit slower. And then again, other things didn't really, at least when I was going through very quickly, I haven't really noticed much obvious difference. Well, in some cases here, for example, here where we are actually looking for specific value inside an HDF5 dataset, it's sort of like a query. The original file was about 40 milliseconds. The page aggregated was only 4. So this is, I think, where these pages that are cached in the library comes into play. But these are like, we're talking about very specific benefits of various commands. But anyway, this is, I just wanted to share these things. This is, as I said, very early on. I literally got these notebooks last week, and I started working on them somehow and try to understand what they do and everything else. And I just wanted to, talk about that a little. Other than that, I have nothing else unless you have some question, or you have some HDF5 related questions anyway, not related to this, what I just showed. Speak up now.
Alexander,
Yes.
when you had mentioned the fact that the chunk size vastly exceeded the chunk cache value, is there any existing audit tool that would have flagged that? Because you said this just goes unnoticed unless you're really looking at it like you are. But I was wondering, is there any existing sort of audit capabilities that would have flagged that? Kind of alert sort of for your HDF5 data?
You mean what HDF Group produces, or in general? I'm not aware of anything.
I would say existing. Is there anything in the current offering of the HDF group that provides that kind of audit capability? I mean, you've rolled your own right here.
No, we don't warn anybody about that stuff.
Okay, so it would really be the responsibility of somebody else to determine that kind of auditing capability.
Yeah, I mean, it's not a library error, right? We don't crash or
Right.
anything like that. You're just not using the chunk cache.
Right. Yeah, you have the freedom to circumvent it. Okay.
I think what you are bringing up is a larger issue that I felt when I started looking about these things, and that is that the library, I think, in its design assumes that whoever is using it knows a lot about the files that are going to be accessed, that you're familiar with the storage settings and things like that, or that your time to optimize and hunt down problems are also indefinite.
Yes.
So you can chase down these problems and have time to spend to basically figure out on your own, regardless to being sort of warned at least of some glaring issues. Maybe H5 stat or some other command line. I mean, the reason why I developed these statistics is because H5 stat was not able to give me this information that I was interested in. And so that's what got me going, in that direction. But yeah, I mean, I was glad that even these 7-8 tables that I, very high level aggregation statistics showed me at least some idea of the settings in the file, and especially 40 megabyte. That's really a chunky chunk.
Yes. Yeah, well, it's clearly, I certainly understand the delineation of responsibilities. It's just not the library. You don't want to put that in the library. So but it's a good separation of concerns that for somebody who is looking for that sort of thing, a higher level piece of software sitting is useful at that point.
Yeah.
So but at the library level, yeah, you're expected to know what you're doing.
And so, yeah, so that was useful. And again, I'm thinking now maybe to do some graphs and things to try to maybe visualize sort of like a graph diagram with all the data sets. And so to show with color, like places where like on Google Maps or whatever maps we have the traffic problems, something red to say to people, look at this data set, there's something to be, to be aware of, just check for yourself and these kind of things also. And again, these files, as I say, they're templated, they're produced in the same way. And so you don't need to check a lot of them to say they're probably all of them are coming up like this with this kind of setting. And so in this setup, the way how this cellular data processing done, just a single sample file done like this, tested, audited like this, can really help in a lot of useful ways. And so, yeah, basically that's what I'm going to explore further and see how far useful things can be derived. And then I'll see also with these files, and there are several other missions that also are kind of known to have detected and experienced these problems with files that are bigger. And so downloading them and moving them around is not that easy, or at least the amount of data really that you want to work with is not movable anymore that much. And what can be done with this cloud optimizing them. This is the most fastest cloud optimization also, because no data sets are rechunked. And you can imagine if you have 4,000 plus data sets that are potential candidates for rechunking, you're not going to chunk easily, rechunk easily if you want a lot more to, if you want to tackle more and rechunk them. So maybe this paged aggregated HDF5 file is maybe this kind of middle ground, because then the library gets file page by file page, and then you have chunks inside this file page. So you get more chunks than you need, but all of those chunks can be cached. And so maybe there is some kind of a good strategy there to do. And yeah, so that's that. Yeah. Any more questions?
No, that's it for me, Alexander. Thank you very much. That's very interesting. Thank you.
All right, thank you. You're welcome. Thank you. And that's it then. If no more any kind of HDF questions, then these sessions continue next week. I don't know who exactly it is, but Lori will will confirm.
Scott, our HPC guy, next week. And of course, any other questions are welcome too. So, all right. Thanks, Alexander. Thanks, everyone.
Take care, everyone. Bye-bye.
Bye, everyone. Thanks for coming.